Thanks for coming to my presentation on feature extraction. I just want to preface this by saying I think feature extraction is strangely unexplored topic in data science. Strangely because I find that it is the most important part of predictive analytics and data science. Feature extraction is the most important part of analytics because it is the key to accurate models. That is important because accuracy is the key to competitive and profitable business. And that's all your stakeholders, clients, and customers care about. So, that's sort of the context for the presentation. So, who am I to speak of these matters? I have quite a long experience doing contextual analysis, or also known as context-based or context-driven predictive analysis. I'm also a social scientist, which I suspect makes me an oddball in this community. I have a PhD in organizational sociology dealing with organizational change, adaptability, and innovation in response to market changes. And in recent years, I've been focusing on the process, organization, and strategy of analytics and data science in the context of business development. And currently, I'm a data scientist at Vattenfall R&D, where my job is basically to push Vattenfall into the future. Vattenfall is a bit late to the data science party. Anyway, in order to keep the abstraction levels low, I'll try to ground everything here in a specific use case, enterprise energy consumption. Starting point here is that Vattenfall has two quite different sales operations for selling energy contracts to companies. And see if this works. Oh yeah, the small and medium enterprise sales deals with energy contracts for companies who consume up to 2 gigawatt hours of electricity per year. So their sales logic is mainly, there's a lot of small standardized energy contracts. The B2B sales operations, on the other hand, deal with big consumers. And those energy contracts are quite complicated and time-consuming and require quite a lot of customization in terms of what kind of energy risks will Vattenfall stand for, and what energy risk will the customer stand for. So, and the logic is doing big but few contracts, which means that the business issue here is when it comes to the addressable market for enterprise energy contracts, the companies on the market need to be allocated to the correct sales operation in order to let their sales processes function efficiently. Thus, this allocation directly affects Vattenfall's rate of customer acquisition, and thus the future market share and revenue. So, big money. And the analytics side of this issue is, of course, to predict the energy consumption of the companies on the market. Thus come back to the accuracy of the model. The accuracy of my models will have a direct effect on the business in terms of money in. And this observation is so important that it deserves a slide of its own. And the general observation is that analytics fuels the business engine. That is an inescapable fact of using an analytics and data science for business development. And in order to drive competitive and profitable business, decision makers need accurate predictions. If predictions are inaccurate, or maybe even wildly inaccurate, well, it will fuck up the business engine. Your business will be non-competitive and unprofitable. So in order to get accurate predictions, we are required to be able to extract the salient features from our data, the salient features that actually hold predictive power, explanatory power for our predictions. And in order to get salient features, we need to have a good domain theory that can describe the determinants, in this case, of energy consumption and the dynamics of those determinants, how they interrelate, how the causal map looks like. So let's start exploring the context of energy consumption, and we'll just take the first immediately obvious facts. So when you talk to domain experts, this is the first thing they'll say. Different industries have different energy intensities. This is a fairly simple measurement. It's basically megawatt hours per employee for a given industry. And the second fact is that bigger companies consume more energy. So if you have two companies within the same industry, the bigger one of those will consume more energy. And the usual proxy for size in this case is number of employees. So we can do a shallow or a simple model on this shallow exploration. So first we get a list of the energy intensity coefficients for all different industries, and then we just multiply a company's employees with the coefficient for its main industry. Now this is basically a spreadsheet level analysis. So this was actually one of the first things I did when I was hired at Vattenfall, was to actually test the accuracy of that model we just saw. And in order to gauge the accuracy, we'll first start to have a baseline for expectations. So if we do a random allocation of companies on the market, knowing that SME companies make up about 74% of the customer base, and the B2B customers make up 26% of the customer base, will get a 62% accuracy when you just do a random allocation. So anyone hazard a guess on the accuracy of the shallow model? Better? Worse? It's catastrophic, actually. So the accuracy is only 50%. And more damning is that the B2B sales operations are the ones who actually need a high quality description of their addressable market, because they're the ones who stand most to lose when they get crap in their sales funnel. So, and actually both of these models, this has a B2B accuracy of just 26%. This is even worse, at 23%. So the B2B sales operations, the list of companies they get allocated to their sales channel will only be 23% correct, which means there's a lot of junk in their sales funnel. So that doesn't fly. So my next task then was to try, well, can we come up with a better model? And I tried various simple regressions on this format. Problem being that the database we had to use was a European database, a market intelligence database done in Bradstreet, and it simply didn't contain enough data. So, and I maxed out at 66% accuracy on this shallow model. So that doesn't fly. And why is that? We didn't use Einstein's razor. And I want to say, this is one of the most profound statements I have ever read on modeling. He said this in 1933. And it's still the best fucking description of how you do modeling to this date. So if you take one thing away from this presentation, let it be this quote. And what does it tell us? So, of course, we want a simple model. Problem is that if we oversimplify it, we'll lose the complexity of the reality of the issue we're actually studying. So, first of all, we have to map the complexity of the real issue, what's actually going on, before we can do then an adequate representation of that complexity when we extract features from our data and plug it into our model. Now, reality is complex. And so by necessity, our feature extraction will need to be complex as well. So let's return to our context here of enterprise energy consumption. These two facts, well, they're still true. And they're huge components of the model, but we have to add a layer of complexity. We did the simple observation that one company can be active in several different industries. And that's why we got so much noise in the shallow model. Because what we have to do here is that we have to divide the employees, the company's employees to each of the different industries they're active in. We have to estimate how many employees work in this industry, and that industry, and this third industry, in order to make a model. Another problem is that there's a lot of industry codes, which means that if you just do all the industries as they are, we'll get a very big and very sparse explanatory matrix of about, I think there are about 600 industry codes. And the sparsity of that matrix will actually dilute the signal we're after. So we also have to do some sort of clustering of the industry codes according to the energy usage. So we're trying to go from this, where we have a list of organizations, number of employees, and what industries they are active in. And we'll have to assume that the numbers are in order of importance. So we have some sort of ranking to actually work with. And then we have to end up with something like this, where we have the organizations and we have the number of employees for the various clusters we have identified, in order to have sort of extracting the features from our data that can actually be sensitive to the fact that companies are active in several different industries. I'm actually fairly proud of this model. We'll see how it works. So when we try to do a model that approximates reality, by this stage, we actually get an accuracy of 85%, which is fairly good, given this is the first version of the model, and there's a lot of complications I haven't told you about, which produce noise in the model. But the best thing is that you get a B2B accuracy of about 80%, which means that the B2B sales channel only get 1 in 5 junk. 4 out of 5 is pure gold. So this is actually usable. And the model itself, well, it's a summary of the actual model I did. Fairly simple. I only use 7 variables. These are my 5 energy usage clusters, and also have capital assets and real estate taxation value. And the model itself is a straightforward linear regression. So the algorithm itself is not an issue. The complexity of the feature extraction is. And I got here by using Einstein's razor, and that's basically about putting the science in data science. So Robert Luciano from Lake Tide earlier said about the divide between computer scientists and the statistics side and the scientist side. I want to make him push for the science side here. Because science is about understanding the complexity of reality. And feature extraction then is about quantifying that complexity so we can put it into a model. The adequate representation of the complexity of the issue at hand. And actually we can expand upon Einstein's razor and get sort of a scientific approach to feature extraction. Starting point being that we'll have to dig for the salient features that are hiding in our data, because they're not immediately obvious. Reality is complex, and so will the features be. And usually you can't data mine them. There's no automated algorithm that can extract the features the time I just showed you. They have to be engineered by hand. And usually you need input from domain experts. You have to work qualitatively to establish a domain theory. So you get a good grasp of the determinants of the issue and the dynamics, the components, complications, complexities, a causal map, and how the different factors interrelate to each other. And I worked quite a lot with domain experts in actually getting the industry clustering going. And of course, what the facts are of enterprise energy consumption. So I knew what to look for. Which is then the next step, is that you can't really collect all the data you need until you know what data you need. And that's what the domain theory will tell you. Only when you have a grasp of the domain, then you know what data actually addresses the issues you're dealing with. Then you can extract the features that represent that model, and you can plug it into your model. So this is the textbook approach. If you look at it as a process, it's rather iterative and messy, because I never start here. I always start with data, and I'll start building models. And they never work. So I have to go to mess about with the data, transform variables, combine variables, trying to extract new features, and see how that works. Usually it takes a while, a few loops in this process of trying out different features, talking with domain expert, getting a good view of how things work. And in the end, I usually end up with a model that I can actually be happy with. So as a process, I tend to iterate through here. And as data scientist, you need to take that time and iterate through the loops to actually get an accurate model that your customers, stakeholders, or clients can be happy with. Because to them, it means money. And I'll leave you with a little data science haiku. Actually, that's I don't know if you heard his question, but he said basically if you have a lot of data, you may not have to be as careful with your feature extraction as I've been, because my data was limited in this case. Problem is that even if you have a lot of data, it's very often the case that the salient features that hold the predictive power for your model isn't one of your variables as they exist in the data set. You'll have to transform and combine different variables and torture them until they actually do anything useful. So having a lot of data doesn't necessarily mean that you'll actually get an accurate model, because you have to inject knowledge, you have to inject your knowledge of the complexity of reality into your feature extraction. Because if your variables don't automatically map to the reality, then you'll end up with an inaccurate model. So I'm just saying that there's a risk that even if you have a lot of data, you won't be happy about it. And when you're dealing with organizational data, almost everything about organizational data is Pareto distributed. It spans over multiple orders of magnitude, which means that, for instance, you'll have to use the logarithmic values to even approach something resembling normality, because that's basic transformation you have to do. And we're talking about multiplying features. That's basically, then what you're actually doing is that you're taking the interaction effects between those two variables and putting that into your model. And that's also something you have to do, because interaction effects will be important as soon as you have a complex problem. Multiple questions. I don't know which one was first. Yeah, you in the back.
Me in the back. Yeah, what are your views on unsupervised learning?
Well, usually when you do unsupervised learning, you do clustering or dimensionality reduction, and that's a good tool. And I use that quite a lot as well, but then you have to be careful with what you're actually putting into the model, because if you don't understand what your unsupervised methods are turning out, you have very little way of actually then evaluating your model, because if you don't understand the features you're getting, you want to understand the results you're getting as well. Of course, you can just test the accuracy, say, hey, that works, but you don't know why. And that's always a bad thing. I mean, I have an example of that. A few years ago, Google had their flu trend diagnostics, which initially was a very good model. It actually trumped the CDC, or the Central for Disease Control's own algorithms for forecasting flu trends. But after a few years, Google's models turned to crap. Somehow, it then failed to predict flu trends because our research behavior changed, because they were predicting flu trends off of our searches, and our search behavior changed, which means that Google's model didn't work anymore. So which means that you have to evaluate your model and see how it works over time. Because if the causal map of your features changes, or the proxies, the process that generates the proxies you're using for data changes, then your model, the accuracy will go down.